All right, let's get set up from the current slide. Okay. Now, didn't want to go over this with you. What was it? There was something else I was going to say. Well, I guess it's just tomorrow. My office hours normally on Fridays are 7:45 to 11:45 on the Birmingham campus. Now, most Fridays I'm there well past 11:45 to my wife's chagrin, but you know, I usually try to get out of there sometime afternoon. But not next Friday, this Friday, tomorrow, or next Friday. I've got treatments both days, and I will be not on campus, either of the next 2 Fridays. So if you are looking for me, please, I forgot the call roll. Sorry. Don't see Zach here, right? And Wayne's not here yet. Nick's not here yet. Tiffany is here. Top of the alphabet, okay? James, not here yet. Parker, not here yet. Lacey, not here yet. Tristan's here. Yeah, I see you. Will, yeah, got it. Jasmine Shante McCrae, we haven't seen from the beginning, right? Okay. Emmanuel's here. Siegfried's here. Michael is here. Patrick is here. Lakeisha's here. Philip is here. Heidi is here. But Amika is not here yet, right? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 2, 4, 6, 8, 10. Got it. Okay. So, got it. Explained about my office hours. Yeah, I guess that was it. It seemed like there was one more thing I was going to say, but I don't remember what it is now. Oh, yeah, I guess it's this. Okay. We got a little behind on labs because we took extra time with the first lab on Tuesday. So what we're going to do is continue in Chapter 2, and then at 5:45, stop and go to lab. Today's lab is much shorter time-wise. It's got a lot of measurements to take, but much shorter time-wise. I think you'll get through it a lot more quickly. Probably have a chance to even turn it in today. You know, it's up to you. You can keep it a week if you want to, but I think you'll finish everything you need today. And then we've already covered the material we need to have covered for the lab. In fact, right now we're on falling objects. We don't have a specific lab for that, but the next thing we cover is two-dimensional things, and the third lab covers that. So we may get close. In fact, I think we'll get into that by the time we our 2.5 hours are over today, even though we've already used 15-20 minutes of it. We could easily be ready for 2 labs, but we only have time for 1. And so that means from now on, it's going to be class, lab, just about every day. We may run into a day that we aren't ready for a lab, but right now it looks like we are, okay? So it's going to go that way for a while. Any questions before we get started? All right. We talked about this last time. I think we covered the information on the slide, okay? And we covered this formula, and I think I gave you the generic form for the formula. Do I need to give that to you again? Or did y'all get it? Y'all okay with it? Okay. This is where we left off last time. Now this is an indicator of this. The distance something falls is proportional not to time, but for the square of the time. So, and the formula we had right here, t is equal to 1/2 at squared. What does A stand for? Acceleration. And when something's falling, what acceleration is that dealing with? What's making it fall?
Gravity.
Gravity, the acceleration due to gravity. That is a constant. Okay, what were you saying?
Oh, no, I was listening.
Yeah, that is a constant anywhere on the surface of the earth. Okay? That means if you're down at the bottom of the Dead Sea Valley or up on top of Mount Everest, wherever you are on the surface of the earth, it's pretty close to being a constant. We use 9.8 meters per second squared. Remember the units for acceleration, distance per time. Okay? Now, if we're in the U.S. customary system, do you know what the acceleration due to gravity is in that system? No, okay. No, not pounds. It would be feet per second squared. It's 32 feet per second squared. In the U.S. customary, 32. If you think about it, remember this is close to 10 yards, not quite, and 10 yards would be 30 feet, right? Well, this is a little bit more than that, okay? 32 feet per second squared, okay? Now, so how do we go about getting these? In 1 second, since the distance that it's fallen is 1/2 the acceleration due to gravity, and since we're using the SI units, System International, that would be times the time squared. 1 second, you square a second, you get 1 squared second, which I don't know what that looks like, okay? But this is meters per second squared. The second squared here per second squared cancel out, and this gives you 1/2 of 9.8. Well, that should be a 1 for up here, okay, not 3, okay? So 1/2 of 9.8 is 4.9 meters. So in the first second, it drops 4.9 meters, which is about 5 yards, right? 4.9 meters, about 5 yards. In the second, you plug in a 2 rather than a 1. 2 seconds, square it, and that becomes 4 seconds squared. The second square cancel out here. 1/2 of 9.8 is 4.9 again, times 4. 4.9 times 4 is 19.6 meters. So in the first second, it drops just over a little less than 5 meters. In the next second, it's dropped almost 20 meters. Just exactly 4 times as far, okay? In the third second, that's the one they showed here, 1/2, 9.8 meters per second squared, times 3 squared, 3 seconds squared, that would be 9. The second squares cancel out, and that would be meters. 9 times 4.9, 44.1. So almost 45 meters in 3 seconds. So you see it's going up by the square of the time. Okay? And in 4 seconds, it would have traveled 78.4 meters, which is about 80 yards. Okay? That's most of a football field. Okay? Down. And if the building were tall enough, it would go even further, but this one's going to crash on the car. So that's why you don't throw things off the top of tall buildings. Okay? The distance is proportional to the time squared. Any questions? And you see that in this formula here. Distance proportional to time squared. What's the constant of proportionality? 1/2 the acceleration due to gravity. Make sense? Now, the next slide shows the velocities. Not the distance, but the velocities. In the first second, now here's your formula for velocity. Final velocity, now this is making an assumption here. The assumption is you're releasing the object from rest. What does that mean? Dropping it. Okay, and what does that mean? What? It's going to be falling. What does that mean? When you release it from rest means initial velocity is 0. Okay? If you were throwing it, then your initial velocity would be whatever speed you threw it with. Then you'd have a different problem. Okay? But if you're releasing from rest, then the final velocity, because the initial velocity is 0, final velocity would be acceleration due to gravity times 7, 9.8 times your time. So in 1 second, it would be going 9.8 meters per second. Okay? The next second, it's traveling 19.6 meters per second. That's why it goes further, because it's picking up speed the whole way down, right? In the next second, it's traveling 29.4 meters per second. And in the fourth second, it would be 39.2 meters per second. That means it's going almost 40 yards in a second. Hey, you don't want to be under that. That's going pretty fast, okay? These best backs that you have, they run a, what is there, 4.4 seconds for the 40 yards. This is going 40 yards in 1 second. It beats even Alabama's running backs. Okay. So, I'm sorry, I didn't say that. Okay. Now, so you see, can you imagine now why has any of you ever been to the top of the Empire State Building? I hadn't either when I was your age, but we went a few years ago with my wife's brother's family, and boy, that's way out there. And they have everything they can do to keep people from throwing things off the top. They have a net around it and everything else like that. Because, why? Lacey's here. That's why. Okay. Because if something were thrown or dropped off the top of the Empire State Building, by the time that reached the ground, that's going to be going at an enormously fast speed. And even a small object, like a penny, going at that speed could give someone a concussion. Yes?
Actually, penny will have the terminal velocity really do anything for units going.
Okay. Because of terminal velocity, exactly. So if you threw something that didn't have the same dynamics of a penny, it could be going even faster, okay? So, but the terminal velocity is what saves you. We haven't talked about that yet, but it's still going at a pretty high rate of speed, and you don't want that hitting you. Or you don't want that hitting a car that's going by down there, causing an accident on those busy trees. Don't want any of that, so that's why they keep people from throwing things off the top. Does that make sense? The speed increases linearly with time, because you see that as a direct proportionality with the time to the first power. Constant proportionality, acceleration, due to gravity. Does that make sense? Okay. Now, it acts like there's supposed to be another slide there. I don't see it. Now, before we go to compound motion, couple of things. What was it? The Summer Olympics that held last summer? It was, wasn't it? That wasn't Winter Olympics. That was summer, wasn't it? Yeah. Summer, okay. I didn't get to see lots of it, but what I did, don't think I ever saw any of the bicycle racing there. But that's an Olympic sport because they didn't show it much. Maybe the U.S. didn't have a good team, so they didn't show the things that we weren't winning at. I don't know. But also, this is true for the Tour de France and these other bicycle races that they have outside as well as these that are inside. Have you noticed the strategy there for bicycle racing?
Yes.
Or any kind of racing, really. Car racing, too. What's that? I can't hear you.
Use the least amount of energy to get the most done.
Okay, and how do you do that?
Well, you pedal up the hills and coast down something like that.
Okay, there's that kind of stuff for sure. But do you want to lead the whole race?
No.
Why not?
Run out of fuel or run out of energy.
Why?
Because you don't have an infinite supply of either.
Okay, but the person behind you doesn't either.
Yeah, but if you spend more energy and more fuel leading going out faster.
Why is that?
Consuming more.
Okay, what if you're going the same speed, he's just behind you?
Drag.
Drag, that's it. Okay? Because of the thing we call drag. And remember we talked about Bernoulli's force? And what the bicyclers do, they have teammates, and the car racers do too, don't they? Don't they usually have some teammate that leads and cuts down on the big guys?
Unfortunately.
Yeah. And unfortunately, the guy who's sacrificing himself, he's not going to win the race. His teammate, the big name, probably will. Okay.
Much less interesting race too.
What's that?
Makes for a lot less interesting race and a lot less actual driving.
Yeah, exactly. So that little blurb is at the top of page 37 in my book, whatever it is in yours. Bicycle Racer's Edge, you can see that. In fact, some of those bicycle racers are almost ridiculous because they go around there just as slow as they can and then pick up at the end and just go as fast as they can. So it's kind of nuts, but they are some of those. And the speed skaters on skating, same type thing, okay? So there's always the jockeying for position and trying to get the edge, like you said. Let's do a couple of the examples here. 2.7 on the top of page 38. Okay, I can't get my pen out. There we go. A rock that is dropped into a well. Now notice it says dropped. Let me get my pen activated here. Okay. It's dropped into a well. I'm going to draw a pretty ugly picture here. This will be our well. You know, here's the bucket and that kind of stuff hanging down here. And the well goes down here and it goes way below ground. Way, 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 way below ground. We don't even at the bottom of it here. Okay? Dropped into a well. And when it says dropped, what does that tell you?
Zero.
Second, what zero?
Release.
Second?
Stop.
Okay. It was so long ago. What was it?
Initial energy.
No, not energy. Velocity, initial velocity. When it's dropped, that means your VI is equal to 0. Okay? Release, dropped, whatever. Okay. Is dropped into a well, hits the water in 3 seconds. So what's your 3-second measure? That's your time. That's a time interval from the time you drop it until it falls. That time interval is T is equal to, is it 3.0? Yeah, 3.0 seconds. Okay? 3.0 seconds. Okay? Ignoring air resistance, which I was trying to get you to do with the Empire State Building problem, how far is it to the water? So we're looking for D. How far? How are we going to do that? What's our formula? Okay, not dividing anything yet. Okay, it's 1/2 of 9.8 times t squared. Now you're giving me the velocity. We're looking for distance. 1/2. The formula is what D is equal to 1/2 AT squared. Okay, 1/2's a constant. 9.8. That's meters per second squared. That's a constant. And your time, 3 seconds. So what would be the distance? D is equal to 1/2 of 9.8 is 4.9 meters per second squared times, and what's 3 squared? 9 seconds squared. You square your units as well. The second squared cancels out the per second squared. That leaves you with meters, a good unit for distance. 9 times 4.9 is, second? Yeah, that sounds about right. 44.1, and that would be meters. But we've only got 2 significant digits here, 2 significant digits there, so you can't have 3 there. We round that to 44. So that's approximately 44 meters. Now, how far is that? Almost 50 yards. That's half a football field, close to it. Down, okay? Good long ways to the water. That would be about 120 feet or 130 feet, something like that. That's a pretty significant. See. Second?
I just said 3.218 times 44.
Yeah. So about 44 meters. Now, there is another way that you could solve that. I think this was the simplest way. But you could find the final velocity, and I don't really like the form. Oh, yeah, right. And the average velocity, and then multiply that average velocity by t. To me, that's an extra couple of steps. This one, pretty straightforward. All right, any questions on that? Okay. Now we move to compound motion. Okay, initially we talked about motion in the horizontal plane. Straight line motion going in horizontal. Then we talked about straight line motion going vertically. Now we're going to talk about motion that's not in a straight line. It's compound. Part of it's going up, part of it's coming down, but part of it's also translating as x. So there's three types of motion. Horizontal motion we covered first, vertical motion we just finished, and then the third is a combination of the two. That's what we mean compound motion. We also call this projectile motion. Okay? Anytime you throw, hit, or do anything else to an object in the air, generally it's going in compound motion. If you are able to throw it exactly straight up, then you have vertical motion. But most of the time it's going to have some sort of an angle to it, and then you have displacement horizontally and displacement vertically. Okay? Now, when you throw an object into the air, let's say, the basic observations are, as long as you got that object in your hand and you're pushing on it, you're exerting the force on it. But the instant it leaves your hand, you no longer got any force on it whatsoever. What's the only force now acting on that object? Gravity. Gravity is all that's there. Gravity acts all the time. Oh wait, does gravity only act when it's coming down or when it's going up too?
Both.
Both, exactly. What's it doing to it when it's going up?
Pull down on
It's slowing it down. And when it's coming down, it's speeding it up. Okay? So gravity is always acting on it. The acceleration due to gravity, and we usually call that the symbol G. Okay? Now that's the parameter, G, standing for gravity. Acceleration due to gravity. Even though it's not an A, it's a G. Don't confuse that with the unit, gram. Gram, you'd have to have a number in front of it. 10 grams, 14 grams, 85 grams, whatever. Okay? This is a parameter, acceleration due to gravity, G. It's independent of the object's motion. If the object's at rest, gravity is still 9.8. If it's moving upward, gravity is 9.8. If it's moving downward, gravity is 9.8. The acceleration due to gravity, independent of the object's motion. Completely. Okay? Now, let's look at this projectile motion. And you've already hit this. If you were able to throw that thing exactly straight up, okay? Exactly, totally straight up in the air, gravity is going to be slowing it down as it goes. As soon as it leaves your hand or leaves the baseball bat or leaves the golf club or whatever, gravity is going to start slowing it down, okay? Pulling down on it. At some point, and we talked about a bullet that you fired into the air, or a ball you throw into the air. It's going up because you're giving it a velocity. But the gravity is slowing that down at the rate of 9.8 meters per second every second. Okay? Every second. It's decreasing that velocity when you throw it up until it reaches zero. At some point, that object will stop moving upward. James, right? Yes. Okay, good deal. All right, goodbye. All right, good to read that.
Pardon?
Okay. So at some point it stops. Okay, because gravity has slowed it down, slowed it down, slowed it down until finally it stops, and then the next instant is coming down again because gravity is still pulling it downward But now when it's coming down, gravity is accelerating it, making it go faster and faster on its way down. So basically, it's going to come down at the same level at just about the same speed it went up. Amazing but true. Okay. The force due to gravity is always acting on the object, pulling it downward, whether it's moving up, stopped, or coming down. The force due to gravity as the acceleration due to gravity. Now, what if you were through something exactly horizontal? Now, I've seen some of these quarterbacks try to do that too. They try to throw a bullet right at the receiver. Now, that's not particularly easy to catch, but it still doesn't work. Why? Gravity's always pulling it downward. You throw it straight that way, by the time it gets there, it's dropped a little bit. Now, it depends on how far you are away. I didn't see the movie Sniper. Did any of you? Okay. It's supposed to have been a pretty good movie. I don't know if it was or not. But I've read enough about the guys who do that kind of stuff, and I guess it could be gals too, but mostly guys. You have to aim considerably above where the target you're shooting for, you're shooting at, okay? Because when they're that far away, gravity is going to be acting on that bullet. No matter how fast that bullet's going, gravity is pulling it downward the entire trip, okay? So even if you were to have a horizontal velocity, gravity's pulling it down. Now here's the key. The horizontal component of the velocity is not going to change, okay? If it started off at 3 meters per second here, even though gravity's pulling it down, it's still going 3 meters per second in this direction. It's just speeding up on its way down. So actually, its speed is going to increase as it goes because that's a combination of the two velocities, horizontal and vertical. Okay? So the horizontal velocity remains the same as long as you can neglect air resistance. That's where the bullets, because they're going so fast, they do have a little bit of air resistance. Now, when you put these two together, horizontal staying constant, vertical decreasing to begin with, increasing afterwards, guess what kind of path you get? A curved path. And we call that curve a special name. Anyone know it? Say again? It is sort of an arc-like shape. It's called a parabola. Okay? Yeah. If you were to watch the time delay of say a basketball when someone's shooting it, a golf ball when someone's hit it, a baseball when someone's hit it. How did the Cubs do last night? I never heard.
They won.
They won. All right, so it's 1-1, huh? It's been so long. Okay, so long. Okay. Every ball that's hit into the air follows a parabolic curve. Okay, that curved path. Okay, that's projectile motion. Guess what? When the firing a missile, dropping a bomb, anything you're doing militarily, following a curved path. Even if it's dropped off a plane, does that bomb go straight down? No. The plane has an initial velocity, the bomb goes like this. So those people who are targeting or aiming that, they have to, and that's why they have computers helping them. They're calculating all this kind of stuff, wind, speed, and all like this. And when they're talking about precision bombing, actually then they probably have something like a laser that's guiding it, to get to the destination. But in the old days, when they just dropped them, they had to calculate all that stuff and hope for the best, okay? So, this is pretty incredible when you think about it. Here the gal is shooting an arrow with a bow, right? Here this lazy guy is just holding the arrow, okay? Now if the instant she releases the bow, he drops the arrow. Which arrow is going to hit the ground first? If it's a level field. Say again? At the same time. Because you see the horizontal component doesn't change. The vertical component is identical. 1 second later, it's got one speed. 2 seconds later, 3 seconds later. Whatever it takes, they're going to hit the ground at the same speed. Of course, hers is going to go way out there. His is going to be right here at his feet. Okay? But they'll hit the ground as long as it's a level field. Okay? Here's another, this sounds unrealistic, and it is, but if you were shooting at, say, you're a really good shot, right? And you're shooting at an apple on the tree, and it's a good distance away, of course you have to aim above it. But if you had some way that who would do this, I don't know, a person would drop the apple at the very instant you pull the trigger, where should you aim your bullet? Above, below, or on it? You do it right on it, because the minute you pull the trigger, that's going to release the apple. The bullet and the apple both fall at the same rate of speed. Gravity acts on them both. That would hit right on. So then you would aim right at it. Okay? I'm not going to be up in the tree releasing the apple if someone's shooting a gun in that direction. Not at all. Okay. But if you had some way to do it, that's right. All right. So firing horizontally or dropping it, they hit the ground at the same time. Now, if she was firing upward, not going to hit the ground at the same time, because it's going to travel up and then down. Now, if he could throw the ball up or the arrow up at the same rate of speed that her vertical component is, then they would hit at the same time. That's really hard to do. All right. Any questions on that? All right, let me make sure I'm not skipping anything. Okay. Did skip a little something here. Let me mention that. There is a little blurb here at the top of page 39 or wherever it is in your book on free fall, and it does take as Tristan was mentioning, turbo velocity is mentioned. In reality, unless you're parachuting on the moon, there is no such thing as free fall, okay? Because anywhere there's air resistance, things are going to reach some terminal velocity or get in the process of reaching it before they hit the ground, okay? I thought this was the one that they talked about some of the records of how high people have fallen from and lived to talk about it, but that's not in this one here. But anyway, it's well worth a read. They also show sort of a dorky looking picture here of someone throwing a ball up in the air and the kid sitting on the limb of a tree, and if the kid were to release the ball at the same moment that ball that comes up to him reaches its peak, he releases it, they fall at the same rate. It doesn't matter. So here's the same type thing we were talking about before. All right. All right, and here's the other example, passing the football. As soon as that football leaves the quarterback's hand, up until that point, he's exerting a force on the ball. The instant it leaves his hand, he's exerting no more force. Now the only force acting on it is gravity, and it's pulling it downward. So we already mentioned this several times. The vertical velocity starts decreasing if you're throwing it upward until it stops, and then the vertical velocity increases. However, the horizontal motion is uniform. If he throws it with a component, say 30 miles per hour up, 20 miles per hour out, 30 slows, the horizontal stays 20, 20, 20. It never changes, so to speak. Now the 30, since this is just roughly speaking, since the acceleration due to gravity is 10 or close to 10, 9.8 meters per second downward, if he throws it with 30 meters per second up, in the first second it's going to be about 20, a little bit more than that. Second about 10. The third second it's going to stop and then start coming down, increasing speed, but all the time, those seconds, 20 seconds, 20 seconds, so it's on 20 meters per second. I don't think anyone can throw a football that hard, but if they could, and that's hitting it with the thing, not throwing it. Okay, so vertical velocity decreases on the way up, stops, and increases on the way down. Horizontal motion, uniform. Combination of the two motions is what we call a parabola. And yeah, okay, this is what it looks like every time. Even if it looks like he's throwing a bullet, it's still following a parabolic path. He's throwing a little up, little down. If he throws absolutely straight, the receiver's going to have to bend down to get it, more than likely, okay, unless it's a very short pass. So all the time, he threw it with a certain velocity upward and outward. Velocity upward decreases, outward doesn't. Upward stops to zero at some point. Horizontal doesn't. Okay? Starts increasing vertically downward. Horizontal still stays the same, and speeding up on the way down. Now, that's kind of assuming a perfect spiral. Okay, and that's what the quarterbacks go for, right? When those place kickers are kicking, or the kickoff men or the punters, they don't usually do spirals, so theirs do some tumbling. Theirs follows pretty much a parabola, but they'll have some other problems with it too. But the passing pretty much a straight thing, parabolic arc. And if they overthrew the receiver, then the receiver has to go considerably higher, or else it's going to go over his head. If they underthrow, then he's going to have to be stooping down or coming back. Okay, but that's football. I'll let Nick worry about that. I'm not going to do it. Okay. So more on this. Well, that's the same thing we had before. I don't know what slide is supposed to be there. Let's see if there is an example. No, I don't see any. So let's move on to, okay, everything we've done up till now is describing the motion. Talking about displacement or distance, speed or velocity, accelerations, one-dimensional motion horizontal, one-dimensional motion vertical, two-dimensional motion compound motion, parabolic motion. We've talked all about describing motion. Now we start explaining the motion. 3 laws of motion, first detailed by good old Sir Isaac Newton. He wasn't quite a sir at the time, but he became one pretty quickly. Did he come up with these by himself? No. Actually, Galileo before him had done most of the work with the first law of motion. Okay, sometimes called the law of inertia. That was almost completely Galileo. But Newton cleaned it up a little bit. He made it more consistent, and he made it tie in with the other 4 laws of motion. The other 2, Newton came up with. No one had even thought about them before Galileo and then Newton. Okay, they all just assumed whatever Aristotle said had to be true. Not. Okay. Now, when he was trying to describe this motion, and frankly, there were several things he was doing at once. There was a colleague or a contemporary of his named, I think, Alex. I'm starting to say Haley, that's not right. Planetary motion. Goodness gracious, why am I going blank on the guy's name? He had described, they had studied the motion of planets, and studied them and studied them and studied them, and he finally figured out some laws that governed those, but he didn't know why. Okay? He knew what the paths of the planets were, he didn't know why. Newton, in his theory, describing the motion, he came up with the why. But you know what? The math that they used at the time he was trying to do that just wasn't sufficient. All you could do was average speeds, average accelerations and stuff. Wasn't really good. He needed something that changed by the second or even more continuously. And he developed a whole new form of mathematics called the calculus. He called it something else. He called it the law of fluxions, whatever that was. But this was the beginning of calculus. And he came up with the law of gravitation. So guess what? Newton, in his very short little lifetime, I mean, he lived almost, what is that, 78 years, is that right? Is that right? Yeah, 78 years, which is pretty old for that day, but still revolutionized motion, came up with the three laws of motion no one except Galileo had even thought of before, developed an entire new field of mathematics, okay, more complicated than any other mathematics before him had ever been done, and came up with the law of gravitation that helped with this too. No one had done that, and we aren't even beginning to talk about what he did with optics and alchemy and all sorts of other things. That is one smart dude, okay? There are few people ever on the planet have done more, you might almost say with less, than Isaac Newton did. Wow. So his essential idea, and really, I'm not sure he ever used the term forces that much. He used a slightly different term we'll talk about later, but that's what we call it today, forces. Okay? So what are these laws of motion? The first one, and this is the one that Galileo did most of, okay, called the law of inertia. What did we say inertia was?
What stays in motion, what's in motion stays in motion, object rest tends to stay at rest.
That's it, the first law right there. Every object retains its state of rest or its state of motion, uniform straight line motion, unless it's acted on by an unbalanced force. See, that's unless it's acted on by the unbalanced force, that's what get them out of Aristotle's quagmire that he was in. Because everything generally is acted on by some unbalanced force at some point or another, unless you're in outer space. But every object retains its state of motion or its state of rest. That's what you were just saying. It's in motion stays in motion, or at rest and stays at rest, unless it's acted on by an unbalanced force. And what the question was, what was inertia? Inertia is that resistance to any changes in motion. Say again? Oh, that's what we mean by inertia. Now here's some examples of inertia, and you've probably all experienced this before. Ever ridden a bus and couldn't get a seat and had to stand in the aisle? Never? Okay. Okay, I have too. Okay? And as that bus suddenly takes off, what do you tend to do? Fall back. No, you're not falling backward. The bus is moving out from under you. Okay? You feel like you're falling backward, but really the bus is moving out. Your inertia tends to make you stay right where you are, but the bus takes off and you tend to stay right where you are. Okay? So if the bus was initially at rest, you tend to move backwards when it takes off in a hurry. Okay? And that's why you hang on to those rods or poles or straps or whatever. Okay? But also, if that bus turns, what do you say it does? You say it throws you into the other wall. No, it doesn't. You're trying to stay right where you're going. The bus cuts in front of you. That's why you hit that other wall. You try to maintain your state of motion, which is straight line motion, and going ahead, the bus turns, and you just bump into the wall, or you feel like you're thrown that way. You're not thrown, the bus turns into you. Okay? Same thing with stopping. Do they have a slide of that? I doubt it, but let's see. No, they don't. If you're going along and the bus stops suddenly, you want to keep moving forward because that's what you were doing, and you feel like you're thrown forward. No, the bus stops ahead of you, and you still try to go forward. Now, I'm just going to hazard a guess that some of you probably have driven a pickup before, right? Yeah. And if you have something on the back of that pickup, and this goes for your car too, especially if it's an SUV and something in the back, and you haven't really tied it down too well or chalked it well or whatever, and you start making turns, that thing gets thrown around in the back because of inertia. It's trying to maintain its current state of motion, whether it's at rest, moving, or whatever, it's trying to maintain that. Does that make sense? Newton's first law. Try to maintain what you're doing. Now let's see, are there any? No, there are no examples on that. So let's go to Newton's second law. It follows from the first law. Now this one, I don't think Galileo even came close to touching. So this is all Isaac Newton pretty much. Now he used the stuff of Kepler, that's who it was, Johannes Kepler. He had developed these laws of planetary motion. But did you know it already?
I was trying to say Hans.
Johann, yeah. But you knew the Kepler part?
Yeah.
You should yell it out to me, okay? I go blank sometimes, okay? So he had something he was going by, but here's the second law, okay? Now, the first law, it tries to maintain its state of motion or rest unless acted on by unbalanced force. So the second law tells you, what does it do if there is an unbalanced force? Okay? An unbalanced force creates always an acceleration. Okay? An unbalanced force, or a force, we also call it a net force, causes accelerations. Always. So you could say the force is proportional to the acceleration. Then you have to get that proportionality constant, and that is your mass. Mass is related to inertia. So these all tie together like crazy. Now let's talk about the units here. They actually give you a unit before they've really defined the thing. I'll go on and define it for you. Okay? Here basically is Newton's second law in a nutshell, in an equation. F equals ma. F standing for force. And by the way, what kind of quantity is a force, you reckon? It's a vector quantity. Direction matters. How about mass? Scalar quantity. A mass is a mass. It doesn't have a direction to it. But acceleration, that's a vector also. Okay?
You say mass was a scale?
Scalar, meaning it's just a number with no direction to it. Just a magnitude. All right. Now, what were our units for acceleration? Do you remember?
Yes.
Typical units. Say again? Meters per second. Per second squared. Perfect. And what was a typical unit for mass? SI?
Yes.
This was on that first test, wasn't it?
That's standards. That's
Mass was? Mass was? Kilograms. Because a gram's so small, they use a kilogram. So here's the unit for a force. A kilogram meter per second squared. That's a lot of units to name. So they made up a new name for that. Guess what they named it? A Newton. Named after Sir Isaac. Therefore, we capitalize its abbreviation. Kilogram's not named after anyone. Meter's not named after anyone. Second's not named after anyone. Newton is named after someone, so we put a capital letter. A Newton. Now, here's the sort of strange thing. Newton really didn't talk that much in terms, if I understand, because he wrote in Latin. I don't read Latin, so I don't have a clue. But my understanding is he dealt with another quantity. We'll talk about it later. And it wasn't so much forces. He talked about another thing. But they still named the unit of force after him. Okay? Now, like I said, we could have said, and I did say, the force is proportional to the acceleration. Okay? What is the constant proportionality? The mass. Change the proportional to an equal times the constant proportionality mass times acceleration. There it is. Newton's second law. What's that? Oh, okay. Now, That means, because they're proportional to it, you exert more force, you create more acceleration. Or, if something's accelerating greater, that means it had a greater force behind it. They're proportional to each other. However, if you had a constant force, what's the relationship between mass and acceleration? Constant force, what's the relationship here? You increase the mass, you decrease the acceleration, because the product has to be a constant. You increase the acceleration, you decrease, well, you can't decrease mass on it. Increase mass with decreased acceleration, and decrease mass with increased acceleration. Okay, and sure enough, you do that. I think they've got the slides out of order here. Let's see if they have it next. Let me clear this out of the way for a moment.
So it's force is proportional to
Acceleration. Right. If you have a force, it produces an acceleration. The more force, the greater acceleration, assuming the same mass. The less force would produce a less acceleration. Like if, you golfers, okay? When you swing that driver as hard as you can, you're going to send that ball, well, if you can hit it straight, send it on out there. When you're putting, you just give it a little force, because you don't want it to overrun the cup. But you can get there, okay? So here's the thing. Now what we called before unbalanced force, now we're calling net force. If you add all the forces that are acting on a body, if you have any excess force, the net force is going to produce an acceleration. Remember my airplane example from last time? If it's flying at a constant speed, level flight, okay, what's the net force acting on it? Zero, because there's no acceleration. However, that plane, when it's taking off, it's accelerating. There is definitely a net force acting on it then. Absolutely. What's that? Yeah, and thrust is what's doing that. More thrust going out here than wind resistance ahead of. That's it, exactly. Now, when I was on an aircraft carriers are so short, and they're sending off planes sometimes loaded with lots of fuel and lots of ammunition. How are they going to do that? I mean, they don't have a long runway to do. You know what they have? They have what is called a, goodness gracious, I can't think of the name. Yeah, catapult. And that's below deck. They got it hooked onto the plane. The thing, it slings that thing off the thing. The engines are running it. Air compression, exactly. Okay.
it's like shoot. It actually just spares it.
Yeah, exactly, and it sort of sounds like that too. Now the jet engines are at full maximum thing. I mean, they're burning blue out the back, and sitting there ready to go. But most of that initially is that catapult throwing you off there. But that's so that when you get off, you can pick up. But every one of them, they dip down and then pick up.
Yeah. So much.
Yeah.
Yeah.
It's really strange. I mean, because that deck is that far above the water, they dip down and then they
drops.
Yeah, it really does.
Because they're heavy in the back.
Yeah.
They just hit well this time.
Yeah.
The gravity from the water, the sea pulls them.
Well, I mean, from the Earth, the gravity is the same everything. It's that they had the deck under them before, pushing against the gravity. Now suddenly they don't, and they have to get enough lift to take them on out of there. So yeah, and then that catapult whams into the end, and you actually feel a little jerk every time. But they have a thing that slows it down pretty quickly. Sort of a lot, unlike the bumpers have that thing that slows down, like if it's hit, that little piston that does it. Sort of like that, only much bigger. Okay.
That also catches them when they come in too, though.
Yeah. Okay. Now you also have
catches them and it drags there.
Yeah, they have, and that's pulling against a friction, and the hook, and that's called, what do they call that? That wire that they have across there. They have a name for it. I was on an aircraft carrier. Yeah, the cable there. Now, If that hook misses,
Oh.
better gun that engine and get on out of there because they're going off the end.
That's right.
So, yeah, they practice that too. Okay. Now, remember I said those jet engines are going at full blue fire coming out of the back of it. Now, guess what? If that was open deck behind them, everybody out there would be fried. Charred and, yeah. So what did they do to keep from burning everybody on deck? They have a thing called a jet blast deflector. When the aircraft goes and gets in position, then this thing goes and raises up like this at about a 45-degree angle. A shield. And then the exhaust hits here and goes upward.
Oh, okay.
Now, if that was just a big metal thing here, that exhaust hit it, it's going to melt it, no matter how big and heavy it is. So that jet blast deflector, that part of the deck that actually comes up like this, they're pumping water through it the whole time, seawater through it the whole time to take the heat away. That keeps it from warping and melting. And guess where my rack was when we were doing night operations? It was just aft of the mechanical room, the hydraulic room that ran the jet blast deflector. So when I was trying to sleep at night, those earplugs in and everything else, every time the plane would come over, you know, and you could feel it when it stopped, and then the jets would rev up to maximum thing, you're roaring just below the flight deck, and then as soon as they took off, you could hear it boom at the end, the catapult, and then the jet blast deflector, boom, you know, right above my head,
You heard
all night long when they were doing night operations. It was miserable. Okay, and I was just aft of that. Yeah, so it was a lot of fun. Okay. And I was on the top rack, just below that flight deck. Just below it. Okay. Force equal MA. Second law, Newton's second law. Okay. What goes there? I don't see it. They do have a little bit of a, well, they show a plane landing, and you can think about all the, boy, that plane looks like it's not even lined up on the runway well, does it? Yo. But anyway, hopefully they get that corrected. Okay. The first law experiment is worth a read here. I think I sort of described an experiment like that to you last time, so you can read through that. Nothing really to do with that. Now, I wish they had these diagrams that you see in figure 220, 221. That illustrates some of this pretty well, but they don't show that until a few slides later. Like I said, they got them out of order. I think one of them's supposed to be right here, but it's not. So we'll pick up that in a minute, okay? Top of page 43, your definition of a Newton, a kilogram meter per second squared. When they have that little dot there, that means multiply, the division line being divide, okay? I think, oh, okay. Here we have, just like we said before, more mass, less acceleration, that's for the constant force, okay? Less mass, greater acceleration if you have a constant force. Ah, good deal. Okay, let's focus on the net force here. Now, what's here? Let's see, they're supposed to have a figure with this. Okay, here we go. Here's the guy riding his bicycle. Okay? Now, what we have here, he's applying a force to the pedals as he's doing, and that force is getting pushed on the road. The tires then push against the road, propelling the bicycle forward. But there's also friction between the tires and the road. That's retarding it a little bit. You also have some air resistance, especially if you're sitting up like this. That's not the best way to ride. How's the best way to ride if you're trying to get speed? Yeah, you're aerodynamic. Just like, what's that? Le Cube, was that a car? I think one of the, second?
I was just repeating what you said.
There was, I think it was a European car called Le Cube or the Cube. It's just a big box. In fact, if you think back, yeah, was that, yeah. Boy, that's not very aerodynamic at all, okay? It's a miserable shape for fuel efficiency.
What's that?
Solid IQ.
The what?
So,
The Scion.
Okay, yeah, that's a Japanese car.
I know about Scion.
It's what?
It's basically a rebadged Toyota.
Yeah, exactly, okay? But it's shaped like a cube. It's got a big block in front. In the Navy, we call that a sail area. I mean, it's just something for the wind to hit against, not very efficient. Guy sitting up on this, not very efficient. So he's going to have a lot of air resistance to go and push him this way, okay? So therefore, the subtle of the friction plus the air resistance, they add down here, and his force applied here, guess what the net force is?
right there, that's 0.
0, exactly. Now, I wouldn't call this applied here and applied here. I'd call this net here, okay? That should be net here. I don't like that they call it applied. This is net force, okay? The net force is 0. Now, if he pedals a little faster, what? Oh, what page? Yeah. Somewhere around 42, yeah. Sorry. Okay? Yeah. If he pedals a little faster and overcomes the friction and the air resistance, what's he going to be doing? Accelerating. Because if the net force is greater than 0, he's accelerating. Okay? But as he accelerates, then velocity picks up, he has more air resistance. So he has to do even more. At some point, he reaches what Tristan was calling his kind of like his terminal velocity. He can't get any faster than what he's pedaling because he has so much air resistance. Okay?
This one's, yeah, he's right.
Right.
No, he's up like this.
Yeah. Yeah, we don't want to show it without me. Okay.
No.
Okay. All right. But if you see these guys who are real serious about their biking, they're in these little tights, you know, they look like leotards or something, but they're serious. Oh yeah, and their helmets. His is just a big old football-looking helmet. They have these aerodynamic helmets. That really makes them go much faster. Okay. So here we don't see any more mass, but what if that was a bicycle built for 2, and his girlfriend back there is not doing any of the pedaling, he's doing all the pedaling, so it's the same force. What's his acceleration then? More or less? Less, because you got more mass, same force, less acceleration. He may still be accelerating, but it'll be less. So you focus on the net force. That's what matters. That's why I wish they'd have said net force here. If the net force is 0, what can you tell me? Does that mean he stopped?
No.
It means what? It means a 0 acceleration, which could be, it would be a constant speed. Constant speed is no acceleration. So he could be going 15 miles an hour, but no net force. Certainly he's applying a force, but the friction and air resistance is equal to that, so he's going at a constant speed. So net force of 0 means 0 acceleration, meaning a constant speed. The air resistance and the tire friction exactly match the applied force result. No acceleration, but a constant velocity. Whether that's 3 miles per hour or 15 miles per hour, still no net force. Make sense? All right. Now, what they don't have is a picture of the bicycle built for 2, and then his gal sitting on it, and look at her feet off the pedals. Shame on her, okay? Doubled his mass at half its acceleration. Okay. Huh? Yeah, it shows it here, but not on the slide here. It'll show up later, and it's out of place. Okay. Here's yeah. Here's a couple things you can do. Remember Newton's second law. This force is usually net force is equal to mass times acceleration. We can write two other formulas that are equivalent to that but different. What would they be?
Accelerate.
Yes, solve for acceleration, then what would you do?
Force divided by.
Yes, force divided by the mass would be acceleration, or the other one would be solve for the mass, and then you would divide by acceleration. So here's all three of them. Net force is equal to mass times acceleration. Acceleration is equal to net force divided by mass, or mass is equal to net force divided by acceleration. Okay? Now those would have to be magnitudes of acceleration. You can't really do the vectors because we're not allowed to do vector division, but same type of thing. Okay. That was really should have gone on the last slide, but I put it here because it had the formula there. Now, before we got to this slide, I'll give you a minute. And remember, you could do the circles or triangles here. Remember I showed you that the first time? The circle, do a dividing line and a multiplication line. Or the triangle. I like triangles a little better. A dividing line, a multiplication line. Okay? Put the net force up here and the mass down here, acceleration here. Net force here, mass, acceleration. Whatever you're solving for, cover it up and it gives you the formula. Force, net force is mass times acceleration. Mass is net force divided by acceleration. Acceleration, net force divided by mass. All three of them right there in one diagram. That works for Ohm's law. It works for all sorts of things. Yeah. Second? Yeah. All sorts of, yeah. Okay. All right, if I take some of this writing off. Y'all got it all? Okay. Now, before I got to that slide, let me get rid of, whoops, wrong thing. Okay, where's my cursor? I mean, I see my cursor, but I can't get, let me do this. Okay. Here we go. I want to erase that. Okay. Let's do example 2.8. A 60 kilogram bicycle and rider, so this is bike and rider, total mass, oh wait, what's that a measure of? 60 kilograms. Nope, not a weight. Mass, yeah, difference between a mass and a weight. Okay, we're going to talk about that later in a minute. That's a mass. They accelerate, so this is acceleration, at 0.5 meters per second squared. Is that a good unit for acceleration? Yes, it is. Distance per time, yeah. So that's your acceleration. Make that equal to. Okay? How much extra force was applied? In other words, what's your net force? When they say extra force, what's your net force? That's what we're looking for. Any way we can get that from the two pieces of data we got?
Yes.
How? Mass times acceleration, MA, and that would be in this case 60 kilograms times 0.5 meters per second squared, and that sure enough gives you 30. Half of 60 is 30. What units? Kilogram meter per second squared, which is a Newton. That's the same as 30 newtons. Perfect. Way to go. Okay? Does that make sense? All right. If you got it? All right. If I take that and erase that one, let's do example 2.9. What is the acceleration? So this time we're looking for acceleration. There's your question here. Of a 20 kilogram cart What's that a measure of?
That's your mass.
That's your mass, okay? If the net force is equal to 40 newtons. Okay, you can go back to your basic formula. Net force is equal to mass times acceleration. Since you're looking for acceleration, solve for acceleration. Divide both sides by mass. That's exactly what you said. The acceleration will be the net force of 40. But I don't want to write newtons down because the units don't work out too well there. What does newton mean? What is its fundamental units? Kilogram,
Time mass.
meters, not mass,
Divided by seconds.
second squared. Kilogram meter per second squared. Divide that by your mass, which is 20 kilograms. Now look at your units. They're your friends, aren't they? Kilograms go out, and that leaves you with 20 and the 40 is 2. So your acceleration is 2.0, I think. No, they just say 2. It doesn't matter. 2, the units are here, meters per second squared. There they are. The units are your friends. They help show you that you're doing it right. That's a good unit for acceleration. Let me tell you this, though, you're not going to keep that up too long, okay? Because you're increasing your speed 2 meters per second every second. So the first second, maybe 2 meters per second. Then the next one will be 4 meters per second. Next second, 8 meters per second. Next second, 16 meters per second. At some point, you're going to be faster than you can possibly go, and you're building up air resistance. So you can't maintain that kind of acceleration too long, okay? Otherwise, you're going to be exceeding the speed of light pretty soon. You can't do that, okay? What's that? Oh, yeah, okay. All right. Why? Oh, okay. I used that slide. Oh, okay. Here we're getting at weight and mass. Okay. And this. Oh, wait. Back up one thing. Concepts applied, a second law experiment. Okay. And I have done something somewhat similar to this in lab before. We're not going to do it. We don't have time, and they're not very precise. But you could do something like that on your own and play around with it some. All right, so now let's move to weight and mass. Now, I heard someone say it today, and it's very common. In most other fields except physics, people treat weight and mass as if they're the same thing. They are not. Mass is how much of an object you have. Weight is the force that is exerted on that due to gravity. Okay? So mass is a quantitative measure of inertia. By the way, it's a scalar quantity. It's the amount of matter you have, okay? My mass is my mass. It's too much, but I've got it, okay? And I'm stuck with it, unless I lose some of it, but, okay. Weight on the surface of the Earth is related to that directly. So that's why we can use them interchangeably. It's the force of gravity acting on that mass. So weight is mass times acceleration due to gravity. Mass is just how much of it is there. Weight is how much force is on it because of that acceleration due to gravity. That mg is a parameter, mass times gravity, that isn't milligrams. You have to have a number in front of it to be in milligrams, so don't get them confused. Okay. Now this g is your acceleration due to gravity, 9.8 meters per second squared, approximately. What's that? mg is the weight. That's mass times acceleration due to gravity. Now, if you saw that following a number, that isn't mass times acceleration due to gravity, that'd be milligrams. Only if it has a number in front of it is a milligram. If it's in an equation like that, that's mass times acceleration due to gravity. We use the same letters for different things. That's a formula. That's not a unit. Now, notice how similar that is to this. Weight is a force. What is this force up here, though? Mass times acceleration, what's that force? The net force acting on an object. That's what's giving the object its acceleration. Okay? Now, weight is not a net force. It is the force that gravity is acting on you as a body. It's your mass times your acceleration due to gravity, or the ball's mass, or the book's mass times the acceleration due to gravity. It's not a net force. That may be part of the total net force, but it isn't. But you see how similar the things are. Force is equal to mass times some acceleration. This is the acceleration of the body. This is the acceleration due to gravity. I'm standing here, the acceleration due to gravity. I'm not accelerating, but gravity is pulling down on me with a product of my mass times the force due to gravity. The acceleration due to gravity, 9.8 meters per second squared, or 32 feet per second squared. So you see the relationship, but don't confuse them, okay? Weight is a force. Now, what's the unit for mass in the SI system? Kilograms. What's the unit for force in the SI system? Force. Newtons, exactly. What's the unit for mass in the U.S. customary system, or the English system? No, that's the weight. Remember, that's one we never use. Don't worry about it. It's slug. You never use it. It's a slug. So we talk about, in the U.S. customary system, we only talk about weight. We hardly ever talk about mass, and yet one of the fundamental units of measurement is mass. We don't use it. In the SI system, we do this. Then the grocery store, and actually on the scales you used in lab, I think, they may have one scale. Usually the upper scale is in pounds and the lower scale is in kilograms. Shouldn't be that way. If they're using mass, it should be kilograms and slugs. Of course, no one would buy any slug in their money. Okay? If they're dealing with forces, then it should be newtons and pounds. But guess what? Nobody understands newtons either. So because this is a constant, G is a constant throughout all the surface of the Earth, therefore you can use them interchangeably. But they're not the same. That's what it's getting at. Pounds and newtons measure force. Those are equivalent units, not the same, but equivalent. Kilogram and slugs are measures of mass, but we don't ever use slugs, so we just stick with kilograms. So you'll see on the things that you buy, all the things I see are liquid. Does your Frito bag, does it have both ounces and grams? Okay, the ounces are measuring weight and the grams are measuring mass, measuring different things. But because this is a constant, you can use them interchangeably. Okay? If it weren't a constant, we can. Now, some point or another here, I'm going to give you a better example. Oh, nope, they got off of it. Let me go on and give you the example now. It's probably going to show up later, but let's do it now. Notice every time I've said G is a constant, what have I always sort of thrown in there? Anywhere near the surface of the Earth, right? What if those astronauts that are up there at the space station now, is their mass the same? Yeah, it's how much they are. Is their weight the same?
No.
No. So you see, weight and mass are totally different things, because up there, the acceleration due to gravity is much less than it is here. Okay? So therefore, they're not quite weightless, but they're much less weight. So there's a good weight loss program, right? Go into outer space. Don't change your mass any, but you lose weight. The trouble is when you come down, you gain it all right back. I mean, you don't gain it, you just weigh more. Okay.
It never went.
All right. Not fair, is it? Okay. In fact, I'd probably come down way more. I don't know. Okay.
Come down with less muscle mass.
Yes, you do. Unless you really work out while you're up there. But even then, you probably do lose some. Yeah? What's that? Yeah, it does. That is one of the problems. That's why they have to exchange those astronauts. I mean, it's not just because they're going to get bored or something. That may be true, too. They've got to bring them down. Otherwise, all sorts of other things go wrong. Inner ear start messing up. They don't have balance yet. They've done quite a few studies on the physiology of weightlessness, and it's not all good. Okay, So they have to bring those folks back down. And actually, there was a pretty nifty experiment within the last few years. Two guys were identical twins. And even though they were grown, they still weighed the same. I mean, they were very close to each other in things. One of them went up as an astronaut, the other one stayed down here, and they tried to keep doing the same thing. When they came down, they started noticing some pretty major differences. Okay? So I think he could get it back, but at the time, just like you say, muscle mass is going to go, you know. All right. Before we get to the third law of motion, let's do example 210 and 211. And I don't think, okay, I'm going to use the same space we did before. I'm going to erase all that. 2.10. What is the weight of a 60 kilogram person on the surface of the earth? So we're looking for weight. And what is that 60 kilogram? What does that measure? What's that a measure of? Mass, okay, on the surface of the earth. They sort of give you a hint there. Acceleration due to gravity, which we call G. What is it? 9.8 meters per second squared. Those are the right units, which is called kilogram is SI, meters per second squared. So what is the weight of that person? W is equal to 60 times 9.8. Yep. That's going to be an 8.
588.
Second?
588.
588. And what units will that be?
Kilograms.
Kilogram is part of it.
Mass.
Meter, not mass. Meter per second squared. If it's got a number in front of it, that's a meter, not a mass. Okay. All right. Now, what is a kilogram meter per second squared?
A Newton.
A Newton, exactly. Or we could say 588 newtons. Here's a problem, though, and this is why the book gives us a different answer. How many significant digits here? 3. How many here? 2. So what your answer got to be? 2. Count over the second digit, then take that and round it up. That makes a 590. That's approximately 590 newtons. Okay. Am I going to take off if you don't round properly? Probably not. If you're in the right ballpark, you'll get credit for it. But to get the answers the book has, this is what you got to do. Does that make sense? All righty. How about 2.11? Everybody got that okay? That's why the book made it 590 rather than 588, because of significant digits. Can I?
Because of what, Dr. Francis?
Significant digits. You had 3 here, but only had 2 there, so your answer can't be more than 2. That's 3, this is 2. The 0 before you get to a decimal place isn't significant unless it has a bar over it or something to indicate it is significant. Okay. Can I erase this and go to 211? All right, let's do that. A 60 kilogram person, that was the same one, wasn't it? What's that a measure of?
Mass.
Mass, okay, yeah. Kilogram is not weight. But he weighs 100 newtons on the moon. Okay. So can you tell me what the acceleration due to gravity is for the moon? Not Earth, but the moon. How would we do that? What's this 100 newton? That would be weight. Okay, say that again. Okay, weight is equal to mg always, and you're solving for g, so divide both sides by m, and that will then give you the g on the moon is equal to the weight on the moon divided by the mass, and the mass on the moon is the mass everywhere, and that would be 100.0. What is a Newton? What units?
It's in kilograms.
Kilogram. That's not all.
Mass.
Meter
Meters.
per second squared divided by, and what's the mass measure? What's that? 60.0 kilograms. So notice the kilograms go off. That gives the acceleration due to gravity. I'm going to cancel some, or divide out some zeros. 10 divided by 6 is the same as 5 divided by 3. So that's going to be 1 2/3. So that would be approximately 1.67 units meter per second squared. See, your units are your friends. They tell you that is a good measure for an acceleration. Guess what? That's considerably less than that on Earth. What's on Earth? 9.8. On the moon, 1.67. It's a much smaller acceleration due to gravity, but it's still there. Okay. Mars would be in between those. Venus would be a little bit less than Earth. You can't walk on Jupiter, but if you could, it would be much bigger because it's much more massive. Most of the other planets are gas giants. They don't really have a surface, a solid surface. The Mercury would have one. It would be much less. In fact, it's probably not far from being what the moon is, maybe 1.7, 1.8. So depends on where you are. Weight is not what they call an invariant. Mass is. Your mass is your mass is your mass wherever you are. Weight depends on what gravitational force field you're in. It varies. Okay. Not just for eating too much either. Okay. Okay. Any questions? Okay. Then I guess we're ready for the third law. Okay. Yes, Newton had 3. Now this one's a little different from the other 2 in a sort of a major way. Okay. The first 2 are always talking about forces acting on one object. The net force on an object, the inertia of an object, the motion of an object. It was always on just a single object. Okay? Newton's third law is dealing with the fact that anytime there's a force, something else has to be involved. The source of the force is some other object. So the Newton's third law relates the forces between 2 objects. The first and second law only talk about forces on a single object. Okay? And here is a statement of Newton's third law. There's several names for it. The one that I find most common is action-reaction. Okay? Whenever 2 objects interact, the force exerted on one object, believe this or not, on one object is equal in size but opposite in direction to the force exerted on the other object. They say that Newton actually did this. Said when you press your finger against the rock is pressing against your finger. Notice here the indentation on my finger. Yeah, that desk pressed on my finger just like I was pressing on the desk. Okay? That's because you're talking about 2 objects, force on one by the other. Now guess what? Who is exerting more force, me or the desk? They're the same. They're the same because they're equal in magnitude, just opposite in direction. It was pushing this way, I was pushing that way. Okay. What's that? Okay. All right. Now, let me give you the sight of the football player here. Makes me think I'll give you the same example later in another context. In fact, that other context and this one very, very similar to related. But I remember when I was probably a sophomore in high school, could have been a freshman. I went to a really small high school, so anyone who wanted to could go out for just about any sport they wanted to. Didn't have to be very good at it, but you could usually make the team if you worked at it. Okay, they let you play, which is what they did for me. Okay. Anyway, I was at that time playing second string defense to the first string offense. And I was defensive end. And we were running sort of, not a major scrimmage, but sort of a scrimmage type situation. And they were running a sweep my way. Not exactly a sweep, but running my way. And got guard, excellent guard, I mean, really good, pulled out and went to block me, and amazingly, I fought off his block, just got past him in time to see Bill Boyce coming full speed right at me. And I was completely stationary, okay? Now, Bill Boyce was our next door neighbor. We lived out in the country. They had the dairy right up the hill from us, okay? Now, Bill never drank much water.
No.
He drank milk out of that dairy container. I mean, at least 190 pounds, and back then I was probably maybe 170 pounds. But anyway, he was coming full speed at me, and I was standing there. Just had time to wrap my arms around him, and all I could feel was his knees just banging my torso. And maybe 5 yards down the field, I did get him down, but it was painful. Okay?
You stopped the force.
Yeah, well, guess what? The same force he hit me with, I had on him, except it hurt me a lot worse. Okay. But anyway, that's the type of thing Newton's third law. Believe it or not. Believe me. Never mind, I won't say that. Okay. Here's another example some of you could probably relate to more than others. Have you ever stepped off of a lightweight bass boat, say, to go onto the dock, but perhaps your friend that was supposed to have tied it up didn't really secure it well? Well, what happens?
Boat goes that way.
Yeah, the boat goes that way, I go into the water. Exactly. Okay? Because the same force with which I push on the boat pushes on me, and if it's got no tie on it, it goes scooting this way, and I go splash. Okay. Now, I have also walked off the deck of an aircraft carrier, given the same force. When I was going ashore, I was on a station in the Navy on an aircraft carrier, go down the plank, to go. Walked off to go off this on the aircraft carrier. Same force I did. The aircraft carrier didn't move at all. Why not? It was huge. It was massive. Exactly. Okay? That's Newton's third law. I exerted the same force on it. It exerted the same force on me. Of course, its mass was huge. Its acceleration minuscule. The bass boat had a very small mass, a huge acceleration. Splash. Okay. That's Newton's third law. The key here is there's always two objects, always two forces. The forces are equal and opposite, but that doesn't mean the accelerations will be equal and opposite. The force will be. Okay, that was Newton's third law. One slide and that's all. They have some better slides in the book. The one with the astronaut and the satellite. Thank you. Okay. If the astronaut pushes against the satellite, and let's say the satellite weighs twice as much as he does, what's the force on the astronaut compared to the force on the satellite?
The same.
The same. But what would be the acceleration of the astronaut compared to the acceleration of the spacecraft, the satellite? If the astronaut weighs half what the spacecraft does, or has half the mass, then his acceleration will be twice what the acceleration of the satellite would be. Okay. So, Before we get to momentum, let's go back one. Goodness, they don't give us any slides, okay? Let's go back to this one and work on a couple more. Okay. Example 212. This is what we were just talking about. A 60-kilogram astronaut, boy, we've had him before, haven't we? It could be a her, though, you know. 60-kilogram astronaut. What's that a measure of? Mass. Very good. This is the mass of the astronaut, so I'll put MA for astronaut. Is freely floating in space and pushes on a freely floating 120-kilogram spacecraft. Okay? That would be also a mass of the spacecraft, or satellite, whatever you want to call it. He pushes with a force of 30 newtons. So the force of the push is equal to 30.0 newtons. Okay? And he pushes for 1.50 seconds. What's that a measure of? That's the time. Okay? Now we got time involved with this too. The A question here, first question, compare the forces exerted on the astronaut and on the spacecraft. What is the force on the astronaut? What would you guess? It said this was the force that he pushes on the spacecraft, so this is the force on the spacecraft would be that. What would be the force on the astronaut? Say again? Yes, it would be 30 also, but to be precise about it, it would be negative 30 because it would be exactly opposite the direction that he pushes on it. Equal and opposite. Now, the book doesn't put the minus sign there. Sort of shame on him yet, but anyway, okay. So they are equal in magnitude but opposite in direction. Okay? Now, and for that 1.5 seconds, that force is pushed. Now, the B part. Compare the acceleration of the astronaut with the acceleration of the spacecraft. What formula will relate those two together? Force, mass, and acceleration. Okay. Okay. What's that basic formula? F equal ma. Now I'm going to do the astronaut first. Okay. And then you can also do the spacecraft. Mass of the spacecraft times acceleration of the spacecraft. We know the force on both of them are 30. We'll forget the minus sign now. Okay. And the mass we know, so this will be 30. Or you want to plug and chug or chug and plug? I started to chug and plug. Y'all may like to do it the other way. Okay, you want to solve for the acceleration? Either way, I don't care. If you're looking for acceleration of the astronaut, what would that be? Divide both sides by mass of the astronaut, right? And this will give you the net force on the astronaut, 30.0. What's the units for a Newton? The fundamental units? Kilogram. Fundamental units for meter per second squared. That's what a Newton is. Divided by the mass of the astronaut, right up here, 60.0 kilograms. Kilograms go out, and that gives you an acceleration of 0.500 to get 3 significant digits, meters per second squared. Okay? Let's do the same thing for the spacecraft. The acceleration of the spacecraft divided by the mass of the spacecraft, Okay? And that would be force on the spacecraft. It's that same 30, but the mass is now 120 kilograms. And that would be, okay, 0.25. 0.250 meters per second squared. I didn't put the units in here, but yeah. Why didn't I put, ooh. I should have put the number here rather than the symbol. That was 120. No, that was the same 30. 30.0 kilogram meter per second squared. And the kilograms go out, and you got meters per second squared. So the acceleration of the spacecraft was half the acceleration of the astronaut, even though they were the same force, because they were different masses. This is like the aircraft carrier and the bass boat. You know, even though it might be the same force on it, acceleration is going to be very, very different. Okay. Now, don't want to lose the numbers here for the next one because it depends on that. So I'm going to have to write somewhere, but that's what we got. Now here, I wanted you to note something here. This had 4 significant digits, but that still only had 3, so the answer can only have 3. That's why they put the extra zeros in there, because you have 3 significant digits everywhere. Okay? Again, I'm not going to take off necessarily for that, but beware of it. Okay. And by the way, y'all keep me up with when we're getting anywhere close to 5:45. I know we're not there yet, but we need to break at that point for lab. Yeah, nowhere close. Okay. So let's look at example 213. After the interaction and the acceleration between the astronaut and the spacecraft, described in 212, that's why I didn't want to erase them, they both move away from their original positions. What is the new speed for each? We know the accelerations for each. This is the acceleration of the astronaut. This is the acceleration of the spacecraft. Okay? So we need to know their, what is it they're asking for? What's the new speed for each? All right, so I think I can erase everything else because I just don't have a lot of room. Okay, so we'll erase this and that and that and that and that and that. I think I can erase it all except for what their accelerations are. Oh, I don't want to erase that. This is the time at which that force was accelerating. In other words, the time at which it was accelerating at that rate. Whoa, you almost let me do it. You weren't stopping me. 0.25. Okay, I can drop those equal signs. Yuck. Okay. Now, all right, here's the assumption. Excuse me. Here's the assumption. When you first push, right before it started, we're going to assume the initial velocity for each of them was
0.
0, exactly. Okay? So, they push with an acceleration of this, and over a time interval of this. So what is going to be the new velocity? In other words, we're looking at V final. And what would V final be? How is it related to acceleration in time? You might want to express the formula in a slightly different way. Maybe this will help. How is acceleration defined? Change of? Second?
Time over distance.
No, that would give you that's related to velocity. Change of velocity over change of time. Okay? And your change of velocity is going to be your final velocity because initial velocity is 0. Okay, final minus initial, but initial is 0. So this means that V final is going to be equal to, multiply both sides, let's just call it T rather than delta T, A times T, acceleration times time. So the final velocity for the astronaut will be his acceleration, which is 0.500 meters per second squared times, what was the time interval at which they were pushing? 1.50 seconds. Multiply those together and you get, that's 0.75. 0.750. See, one of those seconds cancel that out. Meters per second. Is that a good velocity? Yes, it is. So the astronaut's moving away. Now it's going in the opposite direction of the other, so 0.75 meters per second. Whereas the velocity for the spacecraft is also going to be acceleration. This is final velocity for the acceleration of the spacecraft times that same time interval, and that's going to be V final for the spacecraft is going to be its acceleration, which was 0.250 meters per second squared times that same time interval, 1.50 seconds. One of the seconds goes out, and that leaves you with 0.3 V final for space is about 0.375 meters per second. Very good. Okay? Now, they're in opposite directions, so one really should be a minus and one a plus. But here's how you can get away with it. It said speed, not velocity. Speed is just how fast it's going. So that's what it means. But notice they're going in opposite directions. Now, here's the weird thing about this, and it's worth noting, not that probably any of you will ever be in space, but if that were to happen there, and he were to push away, is he ever going to get back? No, because there's nothing to push him back. So either he has a cord attached to him, or else he better have some retro rockets that he can turn on to push him back, or else he'll never touch that spacecraft again. And guess what? They don't slow down. They keep going at that constant speed forever. Forever. Until they get into the gravitational field or something else. Okay. Make sense? All right. Now I think we're ready for momentum. That's this new quantity. And this is one I was really referring to earlier when we were talking about Newton's laws. If I understand it right, I've read about it, but again, I don't read Latin, so I can't go back and read his original text. But my understanding is when Newton was talking about these things, his laws and that type of stuff, he didn't refer to forces. He referred to this quantity of motion. And how he defined the quantity of motion was the mass of the object times the velocity of the object. That was his quantity of motion. That is how we define momentum. An important property closely related to Newton's second law, and frankly, closely related to his third law too, as we'll see a little bit later. This is momentum. Now, where does the P come from? I have no clue. I'm guessing in Latin it may have been spelled with a P. So maybe that's where it came from. But it's P is equal to mv. Now here's a couple of things. Velocity is what kind of a quantity? A vector quantity. Mass is a scalar quantity. No direction. So momentum would be a vector quantity. Okay? Just like force is a vector quantity, momentum is a vector quantity. Now their formulas look a lot alike, don't they?
Yes, they do.
What is F equal to? Net force? Newton's second law? What is it?
Momentum?
No.
No.
This is momentum. What's force equal to? Net force. We used it several times today. MA, mass times acceleration. So you see they're pretty close related. These are both vectors. So this is related to velocity, that's related to acceleration. So in my mind, since Newton focused on this thing, that's what should have been called a Newton. But guess what? Momentum doesn't have a special name for it. You just use kilogram meter per second. All you can call. Well, there is one other. We'll get to it later. But that's an important property closely related to Newton's second law, because Newton's second law is force is equal to mass times acceleration. So they look somewhat similar. It includes the effects of both the motion, that's the velocity, and the inertia, that's the mass. So this is, and frankly, this is a more universal quantity. Just like we were talking about, mass is an invariant, okay? It doesn't change no matter where you are. Your mass is your mass is your mass, okay? Whereas forces, they do change. But guess what? Momentum is also an invariant. Momentum is always conserved. Forces are not. Momentum is. So that may be why, I don't know if that's why Newton used it, but he was a pretty clever guy. He may not have known that was the reason, but he did. Okay? Momentum is mass times velocity. Pretty important formula to know. Okay? Now, here's our picture of the spacecraft. And what were we representing here? Not the second law, but the third law. But we used them both. And here are the numbers we just came up with. The mass of the astronaut was 60 kilograms. The mass of the spacecraft was 120 kilograms. Velocity that we calculated was set 0.75, or 3/4 of a meter per second. Velocity resulting final speed of the spacecraft was half of that, 0.375 meters per second. Now, with those numbers that we did from the last problem example, we could find out the momentum of the astronaut. Mass of the astronaut times his velocity, that would be 60 times 0.75. Do the math, 45 kilogram meter per second. Poor momentum doesn't have its own unit. You have to spell it out, kilogram meter per second. But if we did the spacecraft, mass of the spacecraft was 120. Velocity of the spacecraft we calculated was 0.375. 120 times 0.375. Someone get it with a calculator, see what you get. 120, 0.375. 45.0 kilogram meter per second. See, the momentum is conserved. What it was for the astronaut was the same for this. Why? Because momentum is a vector quantity, though. This would be a negative, that would be a positive. Initially, before you push, what's the momentum? What was the initial velocity? 0. So mass times 0 is 0, okay? And afterwards, you push them apart. This one's going to minus 45, that's going to plus 45. What's that sum? 0. Momentum was conserved. If this one sped up by 1, it all just speeds up the same way. To me, that's much closer to Newton's third law than the second law. Okay? How are we doing on time?
We're doing good.
What is it?
It's like 5:20.
What time we doing later?
Okay, 5:45. Okay, it seems like people are needing to move some, but if we only got, let's go to 5:40. We'll have a 5-minute break, and then we'll do the lab. Would that be okay? Can we make it that long? Okay. If you need to go, go. I don't want any accidents. Yes, ma'am. Hey. Okay. Okay, so let me. Okay, look. All right, we were talking about momentum. Just a quick review. Somewhat similar to Newton's second law in that momentum looks a lot like net force, only momentum is mass times velocity, net force is mass times acceleration. Both of them are vector quantities, meaning directions matter. The difference, one big difference is momentum is always conserved for enclosed system. Forces are not conserved, are not conservative. You have conservative forces, but they are special cases. Okay. We mentioned the conservation of momentum. I didn't get the time. What time is it now? 31. Okay, we got about 14 minutes before we'll do the lab. So, conservation of momentum. I don't know if you can believe this or not, but it's indeed true. Okay? Let's just say you're firing a target rifle, right? Now, there's a bullet that's going to leave that rifle at a very high rate of speed. Okay? Now, the mass of the bullet is pretty small, especially compared to the rifle. Okay? But, before you fire the rifle, what's the momentum of the system? 0. Velocity is 0. The mass is there, but the velocity is 0. Okay? Now, when you pull the trigger and the momentum and the bullet goes flying out of the barrel that way, it has a momentum now, right? The mass of the bullet times the velocity of the bullet. It's a very high velocity, maybe a small mass, but that means the rifle now has momentum this way because momentum is always conserved. It has to be the same. So the same momentum that left there goes back here. Now, if you hold that rifle off of your shoulder and you fire that, what have you got? A bruised shoulder, possibly even a dislocated shoulder. It has happened before, especially some of the really heavy weaponry. It can literally dislocate your shoulder and certainly bruise it badly. Okay? In fact, people coming in for target practice, they didn't have their big bruises sometimes. Okay? Now, so what do we do to prevent that? Hold it up snug against your shoulder. Now, what is that doing to the system?
The system.
Huh?
What is it doing to the system?
System. Now it's not that you're separate from it for it to bruise. Now you're part of the system. So you add your mass to the rifle mass, and there's a lot less velocity backward. So you can absorb that a lot better, but the momentum is still conserved. Okay? So, in this example, the total momentum of a group of interacting objects remains the same in the absence of external forces. Or let me phrase that a little bit better, net external forces, okay? The rifle and the bullet, you really know of it. Sure, gravity's pulling down on the bullet, but yeah, we're not worrying about that here, okay? Now, have any of you ever shot pool? Okay. Now, what's the initial momentum of the system? When you have the rack of balls there, cue ball here, initial momentum of the system is the mass of the cue ball times whatever velocity you give that cue ball. Okay? That's all the momentum is in that one cue ball. Mass times velocity. What is it after the collision? Guess what? It's the same. Because the momentum is conserved. Okay? Which means all that bouncing around that the ball's doing everything else, for every motion that's that way, it's got to be equal that way. For every one that's that way, there's something equal this way. Your total momentum of the system is still in this direction at the mass of the cue ball times the velocity of the cue ball. Now you've given velocity to all the other balls, but the total momentum is the same. Believe me. Okay, never mind. I won't mind that. Okay. Now, I hope none of you have ever been in a car accident before, but I bet you have. Okay? Sorry. When I was freshman at college, freshmen weren't allowed to have cars. My older brother was already at college, but we couldn't afford a car, so we didn't have a car, but he had a friend who was a junior. He was a junior, and he could have a car and did have one. Frank Michelle had maybe a Z28. Nice little car, okay? And it was before classes started, so we thought, hey, y'all don't remember this, Easy Rider? Okay? Easy Rider was playing at the Capri Theater somewhere there in Atlanta, and they said, hey, let's go see Easy Rider. So Frank, my older brother, and me got in the car. I was in the back seat, not much of a back seat on the Z28, but I was packed in there, and they were in front. And Frank didn't know exactly where the Capri was. Mike didn't either, but he had a general idea. Frank was driving a bit too fast and furious. And so here they were going down, and Mike said, somewhere around here, somewhere, we got to watch for it. And Frank didn't slow down any. Mike suddenly said, there it is. And Frank saw him point, so Frank just turned. Well, unfortunately, there was a car coming this way, and Frank just turned right in front. And just behind the rear tire, which was just behind me in the rear seat, on that side, we got smacked, okay? We didn't get to see Easy Rider either. We were doing police report. What were they doing, though? They went out there, and I wonder if it happened in yours, too. Didn't they measure skid marks?
Yes, sir.
Okay, why are they doing that? Because collisions use conservation of momentum to estimate, they don't have it exactly, but to estimate speeds, okay? Well, surely the guy who skidded, trying not to hit us, he was not at fault anyway, but they still had to write it all up. So collisions, they can find a whole lot about collisions using conservation momentum. Analyzing action-reaction interactions. Boy, they got a lot of action in that, didn't they? So there's conservation momentum. All right. Y'all keep me posted on when 5:45 gets here. Huh? 7, 10 minutes, okay. So, before we move on to, boy, they just don't, here's some space. Example 2.14. A 20,000 kilogram railroad car, okay? All right, here is your railroad car. Okay, coasting on a flat level railroad track, and it has its connector up here. So what is that 20,000 kilogram? What's that a measure of? What does kilogram measure? Mass. The mass, and we're going to call this car A, is going to be 20,000 kilograms. Okay? That, by the way, is what they call 20 metric tons. Okay? A kilogram is a kilogram. That's 10 to the third grams. 10 to the 6 grams, which would be a million grams. That's a megagram, which is equivalent to, pretty close to, English ton, so they call it a metric ton. This would be 20 metric tons. So we usually think of tons as being weight. This is mass. Is coasting at 3 meters per second. What's that a measure of? Speed or velocity. So we'll call that V is equal, and this will be V for A is 3. Oh, they didn't put 0.0. I thought, hey, you look familiar. Okay. You just made it in to the first part of the course. Boy, by the skin of your chinny chin chin. No, that's mixing things up there. Okay. What I was going to do was do the eraser here. We don't need the 0.0. They're not using significant digits on this one. I don't know why, but that's meters per second, velocity of A. And it's in that direction. Velocities do have direction. Masses don't, they're scalar quantities. When it collides and couples with a second identical car at rest. So here's another identical car. I probably don't have it quite long enough, something like that. Now, we're using train cars on the level path because those train tracks are not frictionless, but they're pretty low friction. I mean, metal on metal is not very much friction. But this one's at rest. It's identical, it says, meaning it has the same mass. M sub B is also 20,000 kilograms, but it's at rest, initially at rest. What does that mean? VB initial is 0 at rest. This is VA initial, okay? Because you need to know initial and final because momentum is changing, okay? Now, it says when it couples, what does that mean? They come together, but they don't bounce off. They come together, and that's why I put the couplers there, but it does, they couple together. So what you reckon is going to happen? Stop, go backward, or continue going forward? What do you think is going to happen? Continue going forward, but at a slower speed. Yes. The reason is your momentum initially, and this is how you do the problem too. The initial momentum of this system, we'll call it PI, is MA times VAI plus MB times VBI. But VBI is right up here, 0. It's at rest. So all the momentum in the system initially is in car A. And what would that be? Mass times V. Say again? 60,000 kilogram meter per second. Okay? Doesn't have its own name, so you have to write it all out. We'll get it slightly different later. Now, we're assuming no external forces, which means that momentum is going to be conserved. So that means this is also P final for the system. But what is P final for the system? They couple together, and now they're moving along. So what's the final situation of that system? Mass final times velocity final. We don't know this, but we do know this. This is the 60,000. What's the mass final for the system? They coupled together, so you're now at, what's the mass when they couple together? 40,000. So this will be 60,000 is the momentum final, kilogram meter per second is equal to 40,000 kilograms. This time I'm plugging and chugging V final. That's what we're looking for. What is the resulting speed of the combined cars? So how do we get this? Looking for the speed. How do we get it? Divided by, oops, I'm in the way, right? Okay, divided by 40,000 kilograms. 40,000 kilograms. Okay, the kilograms go out. In fact, the 40,000 goes out over here. 4 zeros go out here. 4 zeros go out here. Oops, I forgot to write down kilogram. Kilograms go out here. And what do we have? 6 divided by 4 is the same as 3 over 2, which is the same as 1.5 meter per second. Meter per second. The units are your friends here. Yeah, that's a good measure for velocity, isn't it? Or speed. Meters per second. Now, they didn't give any units, so we'll just leave it 1.5. I mean, any significant digits. So 1.5, 1.5. And that kind of makes sense, doesn't it? Yes.
Where did you get 40,000 from? It's
40,000 because the final mass of the system, when they couple together, now you got 20,000. They are identical in mass, so now the system is both of the cars rolling together, and they got the same velocity. Exactly. Good question. Okay, so your final velocity is, so yeah, double the mass, you have the velocity because momentum is conserved. It has to be the same initially as it was finally, as long as there's no net external forces. Nothing blew up when they joined together, you know.
545.
Is it?
546.
Okay, well, I won't charge you any extra for that minute. Okay, all right.
Better not.
All right. So, guess what the silly book does? They round that 1.5 to 2 because they only had one significant digit. Forget that. I want 1.5, 3 halves, whatever. Don't round that. I mean, that's almost ridiculous.
546.
Okay. Yeah. Thank you.
Yes.
I take it y'all want me to stop. But is that what I'm getting here?
No.
Okay.
He said let you know.
Okay. I appreciate it.
No bad.
The lab's not going to take that long. Okay, we didn't get to do example 2.15. We'll do that next time. Okay? So let me mark where we are, and we'll then move to impulse after we do 2.15. All right, what I'm going to do now is pause. The first thing we're doing is each team is measuring the mass of the 3 balls, either using the weighing pin or not. But see if you can get the mass of the 3 balls. If you use a weighing pin, be sure you zero the scale with the pin on it, and then determine the mass of the balls. So get that first. And actually, this team, since you can't get to the scale yet, you can go on and be somewhere here. Do the second step, which is measure the length of your scale of the run here. Now turn it over so it's the centimeter side. Okay. Go from the bottom here. To there, to the top there, get to the nearest 1/10 of a centimeter.
Okay, now it's just coming up.
On top of this.
Yeah, from the inside to inside. Inside to inside. To the nearest 1/10 that you can measure.
Close enough.
What's that?
That's the length of the scales.
Zero the scale. Put that on there. And then put that on. And it'll only be a few grams. Should be ever so slightly. Okay. Generally, it's a good idea. The one who zeroes it then measures it because he or she knows exactly what they're looking at when they zero it. Y'all determine. Okay. Huh? Oh, just 3. You can't read a point on that. It's just 3 little marks. It's 3 grams. Yeah. A gram is really, really, really light. Okay? Okay. Now, as soon as you got the 3 measured, okay. Determine it's up to you. You zeroed it, so you know where to look. Okay. Now, okay, y'all finished yours? Okay, thank you very much. Y'all want to use the weighing pin or not? I think you do without the weighing pin, right? Okay, zero on the scale. See if you can get the balls about. Each little bitty tick mark is 1 gram. What's that? Okay, yeah. Now here's what you do here. Okay, go from, yeah, you got the right hand on it. Go from there to here and go to the nearest 1/10 of the centimeter. I'll let you walk up. Inside to inside. Okay, throw the balls all over the floor. Okay, no. Okay. Y'all got the masses? 3 and 2. All 3?
Every team.
The red line makes, I'm saying 3.
Okay.
Yeah, that's what he brings up.
Everybody done all three of the measurements of the balls? Okay? Now the track length is inside to inside. Yeah, is there inside to inside. To the nearest tenth of a centimeter. Okay, all through this, right? Okay. Y'all see the wrist on the way?
James Switch and then
Yeah.
I did what I was listening to 60.
Wait, okay, before you start, let me talk about that. Y'all through with this?
16
And this, right? I'll worry about that later. Tomorrow is another day. Y'all finished with the scales and the scales? I'll worry about those things. All right, now here's what we're gonna do next. If you'll check your ramp, they should be set for 5 degrees. Now notice how it's set. It's the lower bar measures that. You see it? The lower edge, the one that's a little bit longer. Okay? Now here's what you're going to do. You're going to, now you take all the balls off the ramp, okay? And you can start with the plastic or the ping pong ball if you want to. Now I suggest that the same person who releases the ball has the timer. The others can record. So let me see your stopwatch, okay? Let me point this out. Your start stop is the button on the right. It's about 2 o'clock. Start, stop. Now, if you read that, it says 0:01 with a smaller 35. What that is 1.35 seconds. That's what that's measuring. To clear it, do the one over here at 10 o'clock, and that clears it. Okay? Don't hit the button in the middle. That changes the mode, and then I have to figure out how to get the mode back. So that's start, stop, and then read your measurement. Clear it, and do the next one. Okay, so listen up now. Some of you took extra measurements last time, and it took us a little bit longer. So here's what you do. I would say go to the back of the other page and record 3 measurements for each ball at each elevation. And it's going to be in seconds, okay? 3 measure for each ball at each elevation. Record them. Now, if one of them seems wacko, way too short or way too long, these are old stopwatches that may have messed up. Redo that. So get 3 that are relatively close to each other. Now, here's the easy part. Throw out the high, throw out the low, and go back to this and put the middle value in seconds. Okay, the time in seconds. You do that for the plastic ball, 3, put the middle value. Do it for the rubber ball, 3, middle value. The metal ball, 3, put the middle value. Then you raise it to 10 degrees. You know how to do that. If you have any doubt, ask me. Okay? Did everybody listening? You heard what to do? 3 measurements. I would put item on the back here. Throw out high and low. Well, make sure they're all close. And then once they're all close, throw out the high and low, and you put the measurement on it of the middle value. Okay? Any questions, please ask. Don't assume something. And maybe we used to have a name for that, but we don't want to go there. What's that?
You said you used to have a name for assuming.
Assume, yeah. It makes the first 3 letters out of U and me. Okay? You never heard that?
I wasn't sure that's what you did then.
Yeah.
Double check.
All right. That's what assuming does. Okay, now one of you teams, the middle team here, y'all have the old stopwatch, so if yours screws up on you, just keep trying. That's fine. Okay. Yeah. It will mess up.
I was doing too.
I
see it.
If you have any questions, please ask. I'm going to shut down Screencast-O-Matic until we go to the next step. Still working on it? Pretty close?
Pretty close, we have two more.
Two more, okay. Go ahead. All right. I should have told you, one of them needs to be a catcher. No, okay.
You can't keep up with it.
Okay. How close are we? One more, okay. All right. They told me it was what? Distance divided by time. What was your distance? Y'all measured it. Front page. Yeah, 43 something or something around there. Divided by each one of the times that you put down, the average time, that little time. So your average speed, same distance, but then divided by the various times. Go down the list until you get them all done. Now, before you go to the next step, stop and ask me. Okay? Any questions on average speed? Sorry, I forgot to record when we said final speed. As I showed on the board, final speed is twice the average speed. Now, what's the next column?
Average acceleration.
Are y'all ready for that yet? Okay. How do you get average acceleration? What's the formula for average acceleration? Say again? Okay, yeah, but we don't have forces. Using velocities.
Change of velocity time.
Ah, very good. Change of velocity over change of time. Okay? Velocity, change of velocity, how do we define that? The final minus the initial over your time period. Let's just call that T. Okay? What is your initial velocity? Initial velocity? Zero. So what your average acceleration is your final speed divided by that time interval that you put in the first column. So it's final, V final, which is the next to last column, divided by the first column, which is time. Right? Good deal. Any questions, please ask. Don't guess. Ask.
Yeah, do you have another one of these lab sheets?
What's that?
Do you have another one of these lab sheets? I
Yeah.
completely wrote something down in the wrong column. I wrote a whole column down in the wrong
Let me
column.
see.
Like I wrote my final speed.
Okay, we got room. Right. I'll find it. Yeah.
Okay.
Okay, you guys, you need to keep up with him, you know?
He said I was wrong.
Huh?
He said I was wrong, so I just let him do his own thing. He said I was wrong.
Okay. So I'm going to